First of all, I would also like to thank the organizers and also the Heraeus Foundation for putting together this workshop. I will give an overview of different data-driven methods for the approximation of the Koopman operator and also of the Koopman generator, and I will show later how we can extend this also to approximate other differential operators, and in particular the Schrödinger operator. And this is joint work with a lot of people shown here, and in particular Felix Nüske. All the parts related to quantum mechanics are joint work with Felix Nüske. And Nelida already gave a very nice overview talk yesterday about Koopman operators and how they can be estimated from data and how they can be applied to deterministic systems and also stochastic systems. So I will go through these slides quickly, but please interrupt me at any time if something is unclear. And then I will spend more time on the applications to quantum mechanics problems later. Okay, so this is an overview of my talk. I will just briefly introduce transfer operators, but I assume all of you are familiar with these operators. I will show how we can use kernel-based methods to estimate these operators from data. Then I will show how we can extend this to approximate the generators of these operators. And I will focus a little bit on relationships between the Koopman operator and the Schrödinger operator. And if I have a little bit of time left at the end, I will show how we can estimate symmetric and anti-symmetric wave functions using symmetric and anti-symmetric kernels. Okay, so just to introduce the required notation here, I will assume throughout my talk that we have a high-dimensional stochastic process, which is denoted by xt here. T is always the time, and it's defined on an RD or a d-dimensional state space. And D can be quite large here. If we, for example, consider molecular dynamics problems, then D is 3 times the number of atoms. If we are working with fluid dynamics problems, then D is basically the discretization of your domain. If you're using a grid discretization, it's the number of grid points, for example. So D can be quite large. And we have these stochastic processes defined on quite high-dimensional state spaces. We assume that there is this probability density, or that we can estimate this probability density from data. This transition density here is denoted by p tau. Tau is the fixed lag time. And then this function p tau tells you that if I start in this point x, how likely is it that I will go to y in time tau? And with the aid of this probability density, we can define these different transfer operators. The Koopman operator was already introduced a couple of times, for example, by Igor or also by Joanna and Nelida. It describes the evolution of observables. Given an observable at time t, the Koopman operator applied to this observable gives you the observable at time t plus tau. You can write it also in this expectation value form. You get the expectation value of observables mapped forward by the dynamics. And if you have a deterministic dynamic system, they can simply drop this expectation value here, and then the Koopman operator propagates really expectation values, observables without the expectation value here. The adjoint operator is the Perron-Frobenius operator, which propagates probability densities instead of observables, but this is just the adjoint, so they contain more or less the same information. And then there's a third operator, which is in the molecular dynamics community often simply called transfer operator, which is just a re-weighted Perron-Frobenius operator. For molecular dynamics problems, we know that there is a unique invariant density, which is given by the Gibbs distribution, and we can re-weight this operator with respect to this invariant density here, and then it's easier to estimate this operator from data. But again, it contains more or less the same information. So we are interested in computing the eigenvalues and eigenfunctions of these operators here, because they contain important information about the global dynamics of the system, for example, about time scales or about metastable sets and coherent sets. And I will show some examples later. So this is these are the operators that we want to approximate, and we want to approximate them from data. So I will look at it from a more data science or machine learning perspective. This was also already shown yesterday, this picture here. So assume we have a finite dimension but highly nonlinear dynamical system. Then instead of analyzing this dynamical system directly, we go to the Koopman point of view here, and we have an infinite dimension operator, but this operator is linear, and we can compute eigenvalues and eigenfunctions. And again, they contain important information about the global dynamics of the system. So this is what we are trying to do here. And then we can also go back to the original state space by expressing the dynamical system in terms of eigenvalues, eigenmodes, and eigenfunctions of the Koopman operator, or also of the Perron-Frobenius operator, for example. We are mostly working with stochastic differential equations of this form here, and later I will show how instead of approximating the operator from data, we can directly also estimate the generator of the operator from data. And for a stochastic dynamical system of this form here, where we have this drift term and this diffusion term, we can compute the generator directly. So the generator is defined by this limit here. We let the lag time tau go to 0, and then we compute this generator here. And for the stochastic differential equation, the generators of this form. This was also mentioned already yesterday. This is the backward Kolmogorov operator here. And the adjoint operator, which is then the generator of the Baron-Frobenius operator, is the Fokker-Planck operator. And if you're interested only in deterministic dynamical systems, you can simply drop this blue part here. So the sigma term would be 0 here, and then you would obtain the Liouville equation. And this, the Fokker-Planck operator, would then also evolve probability densities. And I just want to here briefly point out the relationship between learning governing equations from data and this Koopman generator. If you have this Koopman generator here and you apply this to the observable xi, so that means we are observing only the ith state of our system, then if we apply the Koopman generator, then you can see that all these partial derivatives here are 0 except for the ith one, which is 1. And in this way, we can estimate bi from data. And if we apply this to all of these terms here, xi, then we basically get b. And in the same way, we can also estimate this a term here from data by applying the Koopman generator to these observables here, xi, xj. And this can then be used to learn the drift term and the diffusion term also from data. But we need derivatives. I will get back to that later. But yeah, we might also be interested in directly learning these operators here, or these generators from data. Here I'm just showing an overview of all these different data-driven methods that have been developed over the last year. And I should point out that this is not exhaustive. There are lots of additional techniques based on, for example, Lorentz tensor decompositions or on neural networks. Different methods have been developed by different communities. This is basically developed by here the molecular dynamics community. The same methods have been independently developed also by the fluid dynamics and dynamical systems community. And DMD was already mentioned yesterday. There are nonlinear extensions called extended dynamic mode decomposition. I will focus mainly today on kernel-based variants of these methods, kernel EDMD or kernel TICA, for example. And I will show how we can use reproducing kernel Hilbert spaces to estimate these operators. And these reproducing kernel Hilbert spaces were already introduced also by Ioana and also by Dimitrios yesterday. So this is the same concept again. And I also want to show how we can extend this from this time homogeneous setting to the time inhomogeneous setting. So typically we assume here that the dynamical system does not explicitly depend on the time, but often dynamical systems do explicitly depend on the time. And then we have to go from this metastable set point of view to this coherent set point of view, where we then have to learn slightly different operators from data. And instead of approximating these operators here, we can also directly approximate this generator. And again, I will focus on these reproducing kernel Hilbert spaces and how these spaces can be used to express such operators. And yeah, I already mentioned the relationships between system identification and learning transfer operators or generators from data. Yeah, as a special case, we would also obtain this method SINDI here, sparse identification of nonlinear dynamics, which can be used to learn ODEs or SDEs, given simulation data or measurement data. Yeah, I will first show how we use these methods typically. So we are interested in molecular dynamics problems and fluid dynamics problems. A simple example is shown here. This is now a simulation of the butane molecule. This is a 42-dimensional problem. We have here 14 atoms, and you can see fast oscillations, and you can see slow conformational changes. These fast oscillations are just Brownian motion. We are interested only in the slow changes, which are here these 3 different conformations marked in yellow, green, and blue. And we want to find these conformations from data and also the transition probabilities. So, for example, if I start in this configuration here, how likely is it that I will switch to this one or this one? And you can see already the probabilities here. So with a high probability, we will stay in one of these states. These are then called metastable states or almost invariant sets. And we can also see the probabilities here that we will switch. So this is a Markov state model representation of the dynamics here For this molecule, it's well known that there are 3 stable conformations, but we want to apply this also to realistic protein folding problems, which are quite high dimensional, and we want to estimate, again, these folded and unfolded states from data. In the same way, we can apply this to fluid dynamics problems where we want to find coherent patterns or dominant time scales. And this is a simple example here, or we can also apply this to all kinds of other machine learning problems. So the goal is always to estimate time scales and dominant patterns in these dynamics here. These reproducing kernel Hilbert spaces that we are using for the approximation were already introduced yesterday. So we have a function space which is spanned by this kernel. The kernel is simply a function from the state space times the state space to R. And you can view this as a similarity measure. Given 2 states, how similar are these? And then this remarkable reproducing property is shown here. You can write function evaluations in terms of inner product. So if you want to evaluate this function f in x, we can also write this as an inner product between the function f itself and this representer here, k, fixed in this data point x. If we fix it in one data point, this is a function from x to r. So this is then an inner product in this reproducing kernel Hilbert space. And this corresponds to function evaluation. And then this Hilbert space itself is defined to be the space spanned by all these kernels evaluated in all these data points here. And in particular, we will later need this canonical feature map associated with each data point. So for each data point, we assign it the function k of x comma dot. So the function, the kernel is fixed in this point x here, which means we are embedding our data in this reproducing kernel Hilbert space. I will skip some technical details here, but we can use these reproducing kernel Hilbert spaces and these properties here to estimate transfer operators. And later also we need derivative reproducing properties to learn the generators or other differential operators. Popular kernels are, for example, this polynomial kernel here, shown here, which corresponds to a finite dimensional feature space, or the most frequently used kernel is the Gaussian kernel, shown here. This corresponds to an infinite dimensional feature space. So implicitly, we are mapping our data to an infinite dimensional feature space. We are evaluating inner products in this infinite dimensional space, but we don't have to do this explicitly because we can just use these kernel evaluations. And the Gaussian kernel is shown here. The goal is to express eigenfunctions in terms of Gaussians, or for example, in terms of this Laplacian kernel here. We can express these transfer operators, I will show this on the next slide, in terms of covariance and cross-covariance operators. You can view this as a nonlinear version of a covariance or cross-covariance matrix. The problem is still that these are infinite dimensional objects if your feature space is infinite dimensional. And also, we can't really compute these because we don't have the probabilities here. We can estimate them only from data. So what we do is we compute empirical estimate of these operators. And these empirical estimates can then be used to compute eigenfunctions and eigenvalues of these operators. But everything is really purely data-driven. And then the approximation of transfer operators relies on this proposition here. This expression here on the left, this almost looks like the Koopman operator, and it's basically a representation of the Koopman operator in this reproducing kernel Hilbert space. G would be observable here, Y would be the the state X mapped forward by the dynamical system. And here on the left, you have then this inverse of the covariance operator and this cross-covariance operator applied to a function. And this looks like, if you're familiar with these Koopman operator-based methods, like an EDMD approximation. The only problem here is that this operator is in general not invertible. So typically we have to regularize it, and then we just replace CXX by CXX plus epsilon times the identity. So this is the standard Tikhonov regularization to make sure that the inverse exists. And yeah, we can then express these transfer operators in terms of covariance and cross-covariance operators. This is shown here. I will not explain this in detail, but the goal here is to write these algorithms in terms of only kernel evaluations. Typically, we don't know the feature space explicitly, so we can't really evaluate these operators, but we know the kernel and we can evaluate the kernel. So the trick here is to express these operators in terms of matrices, and then we can compute eigenvalues and eigenvalues and eigenvectors of these matrices, and they then correspond to eigenvalues and eigenfunctions of these operators. So we just have to solve a matrix value eigen problem, and then we obtain these functions that we are looking for, eigenfunctions. A simple example is shown here. This is a quadruple well problem. We have particles which are trapped in this energy landscape here. You can see that they are trying to escape. And the slow dynamics here are going from one well to the other well, or to one of these other three wells here. You can see that after a long time, they are escaping. We have, again, fast oscillations, and we have slow dynamics corresponding to switching from one well to another well. And then you can see these eigenfunctions here. These eigenfunctions contain our information about the global properties of the dynamical system. The first eigenfunction here, this is the invariant density, tells you that with a high probability, we will be in one of these wells here, and with a very low probability outside of these wells. And then these next eigenfunctions contain information about how you can split this state space. For example, you can split it vertically, horizontally, or in this diagonal way here. And then if we combine this information contained in these dominant eigenfunctions, we obtain here 4 metastable sets corresponding to these 4 wells. This is how it's often used in practice, and this is how we can use it to find these metastable sets. We do this for high-dimensional protein folding problems shown here. Here we find folded and unfolded states of these molecules using these reproducing kernel Hilbert space-based methods. And for example, often we are simply using a Gaussian kernel. We can also apply this to video data. This was now the static case, and we now want to go to this time inhomogeneous case. So now these metastable sets can also move in time, and then they are called coherent sets. You can find such sets, for example, in the ocean. Here we have, for example, gyres or eddies, and particles that are trapped in one of these gyres here will stay within this gyre for a very long time and only with a very low probability escape. But these gyres are moving in time. For example, they are now moving in this direction here. These are the so-called Agulhas rings. And then the goal here is now to, again, find these coherent sets from data using Lagrangian data. You can find similar patterns also here in the wake of planes or in space. And yeah, this is just an extension of these methods now to time inhomogeneous systems. And then we can again use covariance and cross-covariance operators. And it turns out that if we do this, we obtain a well-known method, which is called kernel-CCA. It stands for canonical correlation analysis. And using this canonical correlation analysis, we can find coherent sets in these data sets. I just want to show a simple example here. This is the so-called Bigley jet. I will show a simulation. Quickly stop this here. All these blue dots are now particles here. You can see I colored 2 sets here, yellow and red. And if I let this evolve, you can see the difference between this yellow set and this red set. This yellow set is definitely not coherent. It's dispersed quickly. All these particles are escaping. And this red set is more or less coherent. You can see that particles that started in the set will remain in the set for a long time, but you can also see that some particles are escaping. And we can then again use these transfer operator-based methods. They are again based on the Koopman and Frobenius operator framework. And then these eigenfunctions tell you again how you can split your state space. For example, a particle, this is now the first eigenfunction here, the first non-trivial eigenfunction. If a particle starts in this upper half, then it will only with a very low probability go to this lower half of the state space here. And then you can find also these vortices. So this is how these methods are typically used for molecular dynamics and fluid dynamics problems. We are extracting dominant timescales and dominant patterns from data. You can also apply this to more complicated problems. Here we have now ocean dynamics, and we want to find the main gyres again from the data. We have here again the drifters. These are all virtual buoys which have GPS trackers, and then using these data sets we can cluster again the state space, and we can find these main gyres from data. Now we want to extend this to differential operators. Instead of approximating the Koopman operator, we want to approximate directly the Koopman generator. And for this, we can again use reproducing kernel Hilbert spaces, but we need now this derivative reproducing property. We have seen before that function evaluations can be written in terms of inner products, and we can also write derivatives in terms of inner products. This is shown here. It's a theorem that goes back to Zhou. You can also express derivatives, also maybe I should briefly explain the notation here. So alpha here is a multi-index, and we want to compute the derivative of this function with respect to this multi-index alpha here. And we can express again these derivatives in terms of inner products. So we want to compute the derivative of f with respect to this multi-index alpha here. And we can write this as an inner product, where now this differential operator is applied to the kernel, and the inner product with this function f again. So this is again this reproducing property. And we can use this again to derive operators. Before we had this covariance operator and this cross-covariance operator. Now we need operators which encode information about these derivatives or about these differential operators. And this is what we are going to do next. And we need then derivatives of the kernel. So we can see here that instead of applying this differential operator to the function itself, we apply it to the kernel, which means we need all these derivatives of the kernel. If we have this Gaussian kernel, we can easily pre-compute all these derivatives, or we could use automatic differentiation techniques to compute derivatives of kernels. And yeah, then we can learn also these generators from data. We need, again, this covariance operator. I'm using a slightly different notation here. Before we call this operator CXX. This is exactly the same operator again. I call this C00 here, because we don't have data and data mapped forward by the dynamical system anymore. Here we have data and derivatives. For example, you need derivatives of these data points, which you can estimate using, for example, Cramer's Moyal, or you can use finite difference approximations for deterministic systems, which is basically the same. So, and then you need an operator that is related to the action of the generator. This is now for the generator of the Koopman operator. You can see here, this is related to the gradient, and this is related to the Hessian of this function. And then, yeah, we can express these operators, or we can derive these operators, which contain now the action of the Koopman operator. And later I will define the same operator also for the Schrödinger operator, which is then slightly different. And yeah, we can use these operators again to find eigenfunctions. This is a quadruple well problem, again, slightly different here. So we have again 4 wells corresponding to these blue regions here. And we can then apply this method using these derivative reproducing properties to compute these metastable sets. So here we would again splitting of the state space into 4 sets corresponding to these 4 wells here. And we compare this with the Markov state model. We obtain more or less exactly the same time scales and the same eigenvalues, yeah, which are the time scales or related to the time scales. We want to use this now also for quantum mechanics problems. A simple problem is shown here, the quantum harmonic oscillator. And here we want to compute eigenfunctions of the time-independent Schrödinger equation shown here. So this is then the Hamiltonian. And for the quantum harmonic oscillator, the potential is given by this quadratic function here. These are now really numerically computed eigenfunctions, and they are almost indistinguishable from the analytically computed eigenfunctions. So for this one, it's well known that we can compute these eigenfunctions analytically. These are now numerically computed using these operators here. So we estimate these operators from data. We solve then these auxiliary matrix eigenvalue problems, and this gives us eigenfunctions. And here you can also see the corresponding probability densities. We can also apply this to slightly more complicated problems. This is now here for the hydrogen atom. Again, we want to find eigenfunctions of the time-independent Schrödinger equation. Yeah, shown here, this is the potential for the hydrogen atom. And we again use data. So here we use simply uniformly sampled data, and we can approximate these eigenfunctions of the hydrogen atom from data. These are the analytically computed eigenfunctions, so this can still be solved analytically. These are these orbitals, and we obtain the same eigenfunctions, but now computed using these kernel-based methods. In the same way, we could also use this for manifold learning problems. For example, diffusion maps learns the intrinsic coordinates of a data set, and it's approximating this operator, which depends on this parameter alpha here. We could also use these derivative reproducing properties to learn the dimensions of this data set. For example, this is the Swiss roll problem. Here we have 2 main coordinates, this coordinate here and this x3 coordinate. And then these eigenfunctions contain information about the coordinates. So this would be one of the dominant eigenfunctions, and so yeah, colored according to the dominant eigenfunctions. So here we obtain this coordinate here, and here we obtain this x3 coordinate. And then you can unroll this Swiss wall and you get a two-dimensional representation of this, or two-dimensional embedding of this three-dimensional data set. I want to focus now a little bit on the relationships between the Koopman operator and the Schrödinger operator. We have already seen that we can directly solve the Schrödinger equation using these kernel-based techniques, but we can also use well-known transformations of the Schrödinger operator into the backward Kolmogorov operator, which corresponds then to a stochastic differential equation. This is what I'm showing here. So for example, given the Schrödinger equation, the time-independent Schrödinger equation in this case, we can transform this Schrödinger operator into a backward Kolmogorov operator. And for this, we need the ground state. And for this ground state transformation to work, we need it to be positive everywhere. And then we can transform this into this backward Kolmogorov operator here, which corresponds to a drift diffusion process. And then we can apply the Koopman operator-based techniques that I introduced at the beginning to also compute eigenfunctions of the Schrödinger operator. We can use this correspondence here. We can also do this in the other way around. So we can start with the Koopman operator, compute the generator, and turn this into a Schrödinger operator. And then we can solve the Schrödinger equation instead and obtain eigenfunctions of the Koopman operator. But this here really relies on this strictly positive ground state. But this can be relaxed later. And then we arrive at hidden variable theories, in particular Nelson's stochastic mechanics, which is then way more general than this transformation here. But this shows that there are relationships between this Koopman operator framework and the Schrödinger equation, which we also used before. This correspondence between the quantum harmonic oscillator and the Ornstein-Uhlenbeck process, this was also mentioned already yesterday. So you can take this quantum harmonic oscillator, turn it into a stochastic differential equation, and then you can generate data. So here we would again, for example, solve this stochastic differential equation for a fixed lag time tau. And then we can estimate the Koopman operator from this data set. And this then corresponds to eigenfunctions of the Schrödinger equation, always with respect to the ground state. We can also turn the hydrogen atom into a stochastic differential equation, which is shown here. And then we can simulate also the stochastic differential equation. So here we don't have to solve a partial differential equation anymore, but we solve a stochastic differential equation and we generate a lot of data for this stochastic differential equation, apply, for example, EDMD or kernel EDMD to extract these eigenfunctions. And we obtain again orbitals. So in addition to these eigenfunctions that I showed before, we obtain also these eigenfunctions from, again, data now using this stochastic differential equation. And you can see here molecular dynamics potentials and the corresponding quantum mechanics potentials. For example, if you start with this quantum harmonic oscillator, this is this quadratic potential shown here. And if you transform this into a molecular dynamics potential, it is also still a quadratic potential. You can also take, for example, this particle in the box where the potential is 0 within the box and it's infinitely large outside of the box. And then you can turn this also into a molecular dynamics potential, which then look like this. You can do this for all these other potentials as well. So this is now using the correspondence between the backward Kolmogorov equation and the Schrödinger equation, or you can also transform this into a Fokker-Planck equation. And then we can, instead of solving these quantum mechanics problems, we can simulate these molecular dynamics problems instead and compute eigenfunctions in this way. And this is related to Nelson's stochastic mechanics, which is the hidden variable theory. Nelson's stochastic mechanics is based on the assumption that particles are following drift diffusion processes, and you can derive the corresponding stochastic differential equation as follows. So given the wave function psi, which is now a solution of the Schrödinger equation, we write this as e to the r plus is. R is the real part and s is the imaginary part here. And then if we define this osmotic velocity and this current velocity as follows, we take the gradient of this function r here and we take the gradient of this function s, then we can obtain a stochastic differential equation, again of this form, so drift term, diffusion term, b is the drift term, sigma is this diffusion term here, where the drift term is given by u plus v, the gradient of R plus the gradient of S times these constants here. And yeah, the diffusion term is simply a constant, and it's given here by h bar divided by the mass, or the square root of that. So that means that the corresponding potential is now potentially time dependent. So we have this R plus S here. And this is more general than this ground state transformation. For the ground state transformation, we assume that the ground state is strictly positive. If there are nodes, and this was also asked yesterday, then there are certain problems, because then the state space is basically split into several different regions. If you have, for example, a one-dimensional problem and there is a node in the middle, then there's zero probability that the particle will enter the node. So once the particle starts, for example, in the left half or the right half, it will not be able to cross to the other side. And we get two separate STEs describing then the dynamics. So you need an ensemble of particles to then simulate these systems. But again, we can use this more general framework to turn the Schrödinger equation into a stochastic differential equation, and we can simulate this stochastic differential equation. Here, this can be a time-dependent system. Before, for these molecular dynamics problems, we assumed that the potential is fixed and does not depend on the time. Here we have more complicated problems. Everything is time-dependent, and we also have complex wave functions here, which makes it a little bit more difficult. And you can also show that if you have a stationary problem, then Nelson's stochastic mechanics is equivalent to this ground state transformation. And this is shown here. If I quickly go back to this slide here, if you have a strictly positive ground state, that means that this S part here is not required, and the gradient of this S part is 0. So we need only this real part here. And then the corresponding differential equation using Nelson's stochastic mechanics is given simply by the gradient of R. This S term drops out because it's 0. And this is equivalent to this ground state transformation. The only difference here is this factor h bar, but that doesn't really matter. It's just a constant. And we obtain the same stochastic differential equation using either the ground state transformation by turning the Schrödinger equation into a backward Kolmogorov equation, or using directly Nelson's stochastic mechanics. And yeah, I mentioned this already before. Nelson formulation is far more general, and we can use now, for example, these other Koopman operator-based methods also for time homogeneous systems, and I can apply this to Nelson's formulation here. I just want to show a simple example. This is now, again, the quantum harmonic oscillator. And you can see here the wave function itself. The real part is shown in blue and the imaginary part in red. And in the bottom picture, you can see the probability density. So this is simply the wave function squared. And in gray, you can see this histogram. This is now a histogram of the particles which are following Nelson's SD. And you can see that this histogram really matches perfectly the distribution that was here computed analytically by solving the Schrödinger equation. So this shows that this Nelson's stochastic mechanics can be really used to express also time-dependent systems in terms of stochastic differential equations, and that they are really predicting the probability densities perfectly. And now we can also apply these Koopman operator-based methods for finding coherent sets to such problems. I'm not sure whether this has any applications. This was just to show that we can apply these Koopman operator-based methods also to quantum mechanics problems. You can see here all these particles. So this direction here is now the x direction, and this is here the time. You can see that particles start here, and then they follow these different wells. And you can see that then these particles are mixing. But you can still detect coherence. For example, we could now compute coherent sets in these, for such a problem here. And you can also see that the coherence decreases over time. These are now the dominant eigenvalues, and they quickly decrease. And you can see that the coherence is decreasing over time because the particles are mixing. And at the end, after about 6 seconds, you can see that all the particles are mixed and there's almost no coherence left anymore. This was just an illustration how we can apply this to quantum mechanics problems. I will just briefly...
You have 10 minutes.
Yeah, thank you very much. I will just briefly show how we can also directly compute symmetric and anti-symmetric solutions of the Schrödinger equation by using symmetric and anti-symmetric kernels. Before, we used mostly the Gaussian kernel for all of these applications, but sometimes we just want to enforce symmetry or anti-symmetry, and we can do this by using kernels which later look almost like a Slater determinant. I will just briefly, I will not go into the details here. So we take a standard kernel, for example, the Gaussian kernel, and we make it anti-symmetric. And then you can show that if we define a kernel in this way here, so a pi is always a permutation, and if we want this function here to be anti-symmetric, that means if we swap two particles, then the function should have a different sign depending on the permutation pi here. So if it's an even permutation, then it's +1. If it's an odd permutation, then it's -1. And you can show that this Gaussian kernel that we mostly used for the approximation of all of these eigenfunctions can be written as a Slater determinant, which looks like this. And the advantage is that we don't have to go through all permutations explicitly, but we can express this as a determinant. The determinant automatically ensures that this kernel is anti-symmetric. So this can be computed in polynomial time. The kernels look, for example, like this. This is a two-dimensional anti-symmetric Gaussian kernel. This is positive and this is negative here. And you can see that this is really then anti-symmetric. For a three-dimensional space, the anti-symmetric kernel would look like this. You have all these blobs here, positive, negative, and so on. And these enforce anti-symmetry. So you can then learn anti-symmetric functions using such kernels. And you can also show that these kernels are more efficient. You need fewer data points for obtaining the same accuracy that you would need using the standard Gaussian kernel. We can also derive symmetric kernels. The problem here is that we don't have this Slater determinant formulation anymore. We can express the symmetric Gaussian kernel in terms also of matrix permanence. But the problem is that this matrix permanent cannot be computed in polynomial time anymore, but we can approximate it from data. And there are also lots of applications using symmetric and anti-symmetric kernels. We could apply this to graph matching problems, or we used this also, for example, for predicting the boiling point of certain molecules. So these are applications of symmetric and anti-symmetric kernels. We also used it to solve now this electrons in a one-dimensional box problem. If we have 3 electrons and we want to compute anti-symmetric wave functions, then we can directly use these methods that I've shown before, combined with this anti-symmetric kernel, and then we obtain anti-symmetric wave functions. And this is just an illustration how symmetry properties can be exploited and how kernels can be defined which automatically take the symmetries or anti-symmetries in the crowd. But this is work in progress, and we want to apply this to higher dimensional quantum mechanics problems in the future. Yeah, you can also find all of these methods online. These are implemented in Python. If you just want to apply some of these methods to your data sets. And with that, I would like to thank you very much for your attention.
Thank you very much for this nice and illustrated talk. So we have time for some questions. So Dennis, maybe if you want to start.
Stefan, very nice talk. I wanted to ask, so you're working on the quantum applications. So how would, in principle, how would this compare to like a tensor network methods, etc.? Do you have some idea for the futures, like how it will turn out to be?
We have not used tensor methods yet. A colleague of mine, he has this tensor train toolbox called scikit-TT, and he's very interested in using these lowering tensor decompositions. Also, Felix Niske used these tensor decompositions for solving these problems. We have not applied this to quantum mechanics problems yet, but this would be a natural extension, combining kernels and tensor or lowering tensor decompositions. But this is yeah, work in progress. We have not applied this to such problems. We have applied this to molecular dynamics problems and also to some other problems. You can see that under certain conditions, if the systems are decoupled, you can really exploit this low rank structure. But it depends strongly on the system. We typically don't know whether there is a low rank structure, but for high dimensional problems, if there is recoupling, yeah, I think this would be a natural extension.
So I don't know if we have also questions. Maybe let me ask you a very naive question. Which kind of data do you use to do like all this kernel derivation?
We typically really use long trajectories for the molecular dynamics problems. We just simulate one molecule for a very long time, and then we estimate all these objects or properties from these long time series data sets. You can also, instead of using one long trajectory, simulate a lot of different short trajectories. So there are different approaches, and then these operators are always approximated with respect to the density of the data. For example, if you use a uniform sampling, then you obtain the operator with respect to the Lebesgue measure, but you can also sample it, for example, from the Skiff's distribution. This is what you would get if you use very long trajectories. And then the data set is sampled with respect to this invariant density if the trajectory is long enough. And then you obtain also eigenfunctions with respect to this invariant density, which was this transfer operator. So the properties of the operator depend really strongly on the data, and you can use different kinds of data sets. Typically, it's assumed that you really just have a measurement or simulation data, and you don't know anything about the system itself. But these methods, yeah, sometimes really require also additional domain knowledge. If you just apply them to data sets, it's sometimes not really clear what these eigenfunctions mean or how they can be interpreted. But yeah, the goal is really to make this purely data-driven, and you don't need to know anything about the system. It's really just a black box approach.
So, yeah, out of curiosity, I guess you can extend this, like, or combine this with machine learning or like dynamical machine learning. Is there any work in this direction?
Yes, there's a lot of work by, for example, Frank Noé, and we compared also our methods with deep learning-based techniques. So, for example, for this problem here, Frank Noé's group solved the same problem using deep learning methods, and we obtained exactly the same results, or more or less exactly the same results. So these kernel methods are also very powerful, and you can represent almost any function by a linear combination of kernel evaluations. And it's similar to also neural networks, but these kernel-based methods are a flat approach, and these neural networks are hierarchical. So you're just representing your functions in a different way, but you can use exactly the same techniques also to find eigenfunctions of these operators. There's also work by Clarence Rowley and probably a lot of other groups, Yannis Katrakidis, who use these techniques also for learning these operators, approximating these operators from data.
Very nice. Well, thank you very much. I do not see any more raised hands, so I think we can close this. Oh.
Yeah. Sorry.
Sorry. Yeah, go ahead, Johan.
Thank you. Just a brief question about the Nelson dynamics that you showed at some point. First, just on curiosity, did you publish somewhere the simulations or others that you showed, like the video?
Not yet. This is work in progress, and we are still trying to understand all of these relationships in more detail. There seem to be a lot of other interesting relationships between this Nelson stochastic mechanics and also maybe Bohmian mechanics and classical dynamical systems.
And a related question, did you consider this Nelson dynamics for mixed systems and not pure, like, okay.
Not yet, no. But I would be interested in other applications and how this could be used. I'm not familiar with these applications.
Okay, maybe we can exchange at some point, because we are also interested in we got a student who is working on a master student who's working on this at the moment. So
yeah, that would be very interesting. Thank you.
Okay, thank you.